Today I'd like to talk to you about igneous rocks and intrusive activity. This is an introduction to igneous rocks and their landscapes from Chapter 4, Essentials of Geology. To begin, you have to understand that there are three types of rocks that makes up the Earth's surface. These are igneous rocks, sedimentary rocks, and metamorphic rocks. All of these rocks are subject to processes that can change one rock type into another. So whenever you start talking about, all of these processes, the primary thing that you want to focus on is you want to focus on how the rocks actually form and then which processes they go through to change into another. So whenever you start looking at this, of course, the best way to demonstrate it is through what is called the rock cycle. This concept is attributed to, of course, the father of modern geology, James Hutton. What he basically shows here with this diagram is that rocks are continuously changing from one type to another. So if you were to focus on what's going on and kind of put all this together, here's what you want to look at. You want to start to look at the aspect that, let me go ahead and get this started here. We're going to look at the formation of igneous rocks. Whenever you start talking about igneous rocks themselves, they of course form by, in the lower right hand corner, the process of crystallization. What that's telling me is that every igneous rock is going to be a result of either the crystallization of magma, which is found beneath the surface, or it's going to be the crystallization of lava, which is found on the surface. Okay, so understanding that right there is a key process, because if you start picking up rocks and you look at them, igneous rocks tend to have the clue that they are going to be made out of crystals. Now that's not always the case, but we'll address that in another lecture. Well, if you were to take this igneous rock and expose it to weathering, what's going to happen to that rock is it's going to break down into its constituent minerals. Those minerals are of course going to be transported as sediments. They're going to be deposited, and then through the process of lithification, they are going to become sedimentary rocks. Lithification is just a fancy geologic name for the compaction and cementation of rock, or of sediments into sedimentary rocks. So lithification is how we make them. We lithify sediments by either burying them and having overlying layers compact them together, making the rock, or you have a cementing agent holding the sediments together. The three most common types of cementing agents that you're going to find with sedimentary rocks are, of course, calcite, silica, and iron oxides. So now you're going to take that and you kind of get a better understanding of, I've broken down this rock, this original igneous rock, into sediments, and those sediments were deposited and then made into another type. Well, if I were to take those sedimentary rocks and apply heat, pressure, or chemically active fluids, what I'm going to do is then take that pre-existing rock, in this case sedimentary rocks, and make it into a new type of rock. Okay, well, by looking at this is through the process of metamorphism, and what you have just made is, of course, a metamorphic rock. Okay, so what you see here is we've kind of gone around the outside and we've made three different types of rock through three different types of pressures. 1, crystallization, 2, lithification, and then 3, metamorphism. And those three processes make three different types of rocks. The thing that I want you to understand, though, is that you can also take a pre-existing igneous rock and make it into another igneous rock. All you have to do is remelt it, and then it'll make a new igneous rock. You could take an igneous rock and transform it exactly over to a metamorphic rock. Okay, a perfect example would be taking the igneous rock granite that is depicted by this symbol right here. This represents granitic rock, and through the process of metamorphism, I can change that into what is called a gneissic rock, or gneiss, G-N-I-E-I-S-S. Okay, and then of course you can take a sedimentary rock, uplift it, expose it, weathering could occur, and you can make a sedimentary rock. So the primary thing that I want you to understand about, the rock cycle is every type of rock can make any other type of rock. It can go in a complete circle on itself, or you can go through simple processes. I can take sedimentary rock, melt it, and make igneous rock. I can take sedimentary rock and make sedimentary rock. So it's kind of like one big messed up circle, as you can see depicted here. All right. So now that we have a thorough understanding of the rock cycle, what we're going to do is we're going to shift our focus into igneous rocks. That's going to be the primary purpose of this whole lecture. But before we get started with that, what we have to do is we have to look at how do these things actually form. And of course, we've already discussed that they are formed through the process of crystallization. Well, to get a thorough understanding of igneous rocks and their formations, you first have to understand some factors that are going to influence the formation of magma and lava. Okay? Well, of course, whenever you start talking magma, you're talking about material, molten material that is beneath the surface. And if that material that comes from deep below extrudes onto the surface, then it is simply called lava. So it's the same stuff. It's just depend upon where it's located. Well, whenever you look at magma or lava, there's actually three components of it. You have what is the liquid part called the melt. You have the solid part, which are certain minerals that have already crystallized. And then you're going to have the gaseous component called the volatiles. These are three major parts of a magma. And, understanding that, you're going to start to see how these things go about making igneous rocks. All right. So the first thing that we have to cover, and this is one thing that's kind of, it's very important in the development and understanding of igneous rocks, is we have to understand what influences the origins of magma, okay? Of course, because this is a foundation of understanding what forms igneous rock. Well, looking at it, we have four basic factors that are going to influence this magma. Temperature is one of them, pressure, water content, and volatiles, and the composition of the actual rock itself. So whenever we're looking at this, most magma is going to originate when rock and the solid crust and upper mantle are melted. Okay, so one of the easiest ways to actually melt this rock is to take it deeper. As you can see over here, we have what is called the geothermal gradient. With the geothermal gradient, that basically says that as you take rock deeper, it's going to increase the actual temperature. Okay, and so whenever you start talking about this, you're then going to be able to melt the rock. And of course, if you melt the rock, that rock can turn around and crystallize and make igneous rock. So that's why we're taking this primary focus here on the origins of magma first. So looking at this, here's what's happening. At convergent boundaries, you have the oceanic plate. In this case, we'll talk about an oceanic to continental convergence. An oceanic plate is going to go in and subduct underneath of a continental plate. Well, as it subducts, of course, the temperature is going to be raised on that. Well, what ends up happening is the temperature on the rock then takes this solid lattice, and what it does is it basically breaks the lattice. Increasing temperature vibrates atoms, and you can end up breaking the bonds. And as soon as you start doing this on pre-existing rock, that rock is now melted, and now you have the origin of magma. Okay, so whenever you start looking at this, you can also have some of the melting occur when rising bodies of hot material essentially bake the nearby rock. So as you can see on the diagram on the right, as this magma is rising up through, what it's going to do is it can actually bake some of this pre-existing rock and actually generate more magma. And with that generation of magma, of course, what are you going to have? You then can have the formation of igneous rock bodies. Okay? All right. So temperature, just by simply increasing the temperature, which I have a big typo there, which will be fixed. By increasing the temperature, we can actually melt rock. Okay. The second thing you want to look at here is now we're going to look at pressure. Whenever you start talking about pressure and its influence on the origins of magma, you really want to focus on something like a divergent boundary. Okay, down here, you have magma that is exceptionally deep, and that magma is, of course, rising because it's less dense. Well, because the pressures are so great down here, what it does is those bonds actually stick together. So you have increased pressures holding the bonds together. Well, as soon as it starts to rise up through the actual crust and through the upper portion of the mantle, what ends up happening is you have less pressure on it. And as soon as you remove the pressure from that area, then the temperature component takes over, and that magma will actually, that rock will melt. Okay, so you've generated magma by something called decompressional melting. You have a solid body moving up. Okay, so its solid mantle rock is going to ascend, and then as it does, pressure is released, the lattice is broken, and then you have a liquid magma generated. And of course, in this case, that liquid magma is going to come out onto the surface through the crust, and then it's going to recrystallize, making new igneous rock right there. Okay, so decompressional melting is very common along divergent boundaries. All right, the third factor that's going to influence the melting of pre-existing rock to make magma is adding volatiles such as water. What this actually does is by adding water into these rocks, the water acts as what is called a flux. Okay, a flux is like a catalyst that'll speed up a process, and then in this case, you add water to the rock. What it's going to do is it's going to lower that melting point. It's going to decrease the melting point and allow the rock to melt. So adding water to rock allows it to melt. Well, of course, where is this most common? At subducting boundaries. What you have going on over here is you have this oceanic crust, which is, of course, basalt. It's going to have a high water content. As it subducts, the temperature rises on it, and it's going to release water to the surrounding rock. Okay, well, by releasing that water to the surrounding rock and actually just having that whole area become what is called wet rock, okay, what's going to happen is you're going to drop that melting point. So if this were typically going to melt at 900, by simply adding water, it may start to melt at 800 now. Well, of course, whenever you do that, you generate magma. Magma is less dense, it's going to rise, and then you're going to get igneous rock bodies forming. Okay, so what we're looking at there is we're looking at the third component that can influence the origins of magma, which then, of course, create igneous rock. All right, so that's three of the big ones right there. This is you've got temperature. So if you have an environment where you can increase the temperature, you can melt rock and make magma. If you have an environment where you can release pressure, you can actually create magma. And then, of course, if you have an environment where you can add volatiles such as water, you can make magma. Now, the fourth thing that you have to look at is you have to go back to something called Bowen's reaction series. Okay, with Bowen's reaction series, what this basically tells you is that through the experimentation of N.L. Bowen, what he recognized is that certain minerals crystallize at different times from a melt. So if you start taking this actual melt and say, all right, I'm starting to cool it down. So this temperature is 1,000 degrees. Well, now I'm going to start to cool down my magma. What ends up happening here is you're going to see olivine crystals come out first. So you're going to have olivine solid crystals inside of a liquid melt. Okay? And then, of course, the olivine then can react with the remaining melt. And what you do is you end up with pyroxene. And then you keep on getting these minerals coming out. Okay? So as you can see, quartz is the last to crystallize from a magma. Now, this is a big deal. We'll talk more about Bowen's reaction series whenever we get into the igneous rock component of the lecture. But just for this part, just realize here's what happens. This is from a crystallizing melt. You have olivine come out first, pyroxene, amphibole, biotite, potassium feldspar, muscovite, and quartz. Now, we're talking about melting though. Whenever you start talking about melting, let's say that we have a rock that is made out of all of these minerals, just to make it kind of, simple and so you can understand the concept. What's going to happen is if we were to apply increased temperature to that rock, so high temp is going to be exposed on this rock. What you're going to notice is it's going to start to melt the minerals at different times. Okay? So the first mineral that's going to start to melt whenever I increase the temperature, let's say it was subducting, quartz is going to melt first. Everything else is going to remain solid. and then muscovite mica will start to melt as I continue to increase that temperature as it subducts. Then potassium feldspar, biotite mica, etc., etc. So what you're looking at is you have to look at what the original rock is made out of to determine when it's going to melt. And then once you actually do that, then you're going to, have the components to make a new igneous rock. So what we're looking at here is we're looking at 4 primary processes that actually cause the formation of magma or lava, which of course crystallize to make igneous rock. Okay, so whenever you start looking at this, this is the whole concept of it. When magma cools and crystallizes, the silicon oxygen atoms link together, first forming the silicon oxygen tetrahedron. Of course, the silicates are the most abundant mineral group, so of course a lot of our rocks are going to be made out of silicate minerals. And as this magma continues to cool, this allows the chains to actually join, and then the earliest minerals have space to form and develop, and then the last minerals form and fill the void and creating cracks. Okay, so basically what it's saying here is if you were to look at a piece of granite, the reason that the orthoclase is so big and the hornblende is so big crystals is because they have a lot of room to actually form. Then what's of course last to cool, according to Bowens? Quartz. Quartz is going to fill in those voids. So if you were to look at a piece of granite and with a hand lens, you're going to notice that the quartz crystals are a little bit smaller when compared to the hornblende and the orthoclase. Okay, so that concludes the lecture on the origins of magma. The next lecture is going to be looking at the formation of igneous rocks.